A couple years or so ago, I did a video on the Sabtronics Model 2000, which was the flagship product of the Sabtronics company out of Texas. And it was probably one of the first, if not the first, affordable to the average hobbyist anyway, digital multimeters. This came out at a time when all the competition, including, either current or upcoming ones from Heathkit, for example, were considerably more money. This weighed in the high 60s as a kit, or that's $60, $69 or whatever it was. And it was actually a pretty good product. The ranges were a little limited. There's only 4 ranges, although in reality it's 6 ranges because it jumps in 2 orders of magnitude between buttons. So it goes, for example, from 100 millivolts to 10 volts and then to 1 kilovolts. If you want the 1 volt range, you put it in the 1 millivolt or 100 millivolt and then push the times 10 button. And if you want a 100 volt range, you put it in 10 and push the times 10. And I don't think you can do that with the 1 kilovolt range. Anyway, this is a pretty decent product, and I acquired one after losing or discarding the original one I had. And I always wondered what the frequency counter companion was to this. There was a frequency counter that went with this. And there was also a newer version of the 2000. I don't recall if it was also called the 2000 or if they added A at the end or something, or just added a slight increment to the model number, but it was essentially the same. They tweaked a couple of things. I think they improved the battery life or something, and they had graphics that had some color on them instead of just the black and white graphics, but pretty much the same product. Anyway, after years of looking, I finally found one of the frequency counter equivalents to this multimeter, and that's the subject of this video. This product is the Sabtronics 8110A ASM. The ASM, I believe, means assembled. I bought this from a eBay seller in the United Kingdom, and they said that it was still in the original box, bought new, never used, etc. And there was no indication of them having built it. And then when I saw the ASM, I knew this was one that was factory assembled. So the thing just arrived. It took a long time to get it over from the UK. So there's a little bit of an unboxing here. It has the Sabtronics manual. And it has what looks to be some addendum sheets and things. What's it say here? Daram Supplies, Warrington, Cheshire. Purchased by T.M. Hayes, Esquire. Is that Cardiff? I don't know. 1 frequency meter, 67 pounds. Purchased in 1982. There is a Sabtronics sticker, making performance affordable. And at that time they were in Tampa, Florida. They had moved from Texas to Tampa. And there's a illustration booklet with the schematic and some circuit board diagrams and things. Very Heathkit-like in this regard. Then a 1-year limited warranty for the UK and Ireland. And then the actual meter. So here's the front of the frequency counter. It has the same kind of color scheme that the slightly later models of Sabtronics units had, as I've already mentioned. The The switches are a little cheap. Instead of toggle switches or rocker switches, it just has little slide switches. There's 3 gates, 0.1 second, 1 second, and 10 seconds. There's a 3-position range switch and the power switch. Kind of wish they'd use push buttons for that, but okay. And a BNC connector for the input. Not a lot of stuff on the front of a frequency counter. And there's the rear of the unit. It has a marked external input, and that's kind of odd because it's not an input, it's power supply. Makes you think you could hook a signal up to that. It's a little weird. And then taking this cover off by sliding the latch over, which doesn't even have a detent on it. It's kind of... And there's a holder for 4 C cells. Doesn't seem to have experienced any leakage. Since I don't have a power adapter for this handy, I'm just temporarily slapping in 4 alkaline C cells. So here's just a quick test. I've got my old Hewlett-Packard 3312 function generator hooked up, and it's currently on a triangle wave, or I'm sorry, it's on a sine wave output, and I have it set to the 1K range and 1 on the frequency dial, and I'm in the 10 megahertz range on the switch here with a 1 second gate time. The flashing LED indicates the gate. Every time that happens, we get an update on the display. And I'm getting roughly 0.001 megahertz, which is 1 kilohertz. So that seems to be good. If I go up to the 10K range, I should expect to see the same thing, but 1 decimal point over. And I do. And 100K, same thing. 1 meg, and that all seems to be working pretty well. If I go up to about 4.5 on the dial, pretty close. And I can probably overrange it by going almost up to 10 on the dial, and it does display there. Maybe it'll go up to 99 on here. This is about 13 on the dial, so that's working. If I go to the 100 meg position on the switch, yeah, it's still reading about 13, which is what the function generator is putting out. So that's all working as a quick initial test. And with the function generator turned off, I go to a display of all zeros. So basic functionality is confirmed. I'm not sure exactly what this is. PSC. Does that mean prescaler? The manual only has 1 page of operation and 1 page of specifications, and this is the whole operation manual here, just this 1 page. And it suggests that I should be able to change the resolution in a 0.1 hertz to 10 megahertz range, a 1 hertz to 100 megahertz range, that would be these 2 on the right, and then a 10 hertz to 600 megahertz, but that's on the model 8610A. So, and the diagram here suggests that it should say 600 on the front, but that's presumably only the 8610A, not the 8110A. So I'm not sure about that PSC. Now the the schematic diagram does make reference to a 100 or a 600 megahertz prescaler. I don't know. It's almost like this is the wrong schematic. I'll investigate further. One thing that Sabtronics did improve, their initial versions just had a plastic rail here and a plastic rail here which were glued on, and they did have two little bumps on them that went into holes, but you basically had to sort of epoxy them on here. And then the wire bail kickstand went in much as this does, but every time you tried to spring it up, it put so much pressure on the rails that it would almost snap them off the bottom. And the rails themselves made kind of poor feet for setting it on if you had the bail folded down. So I do know that on later versions they abandoned that rail and went with these more substantial combination feet and bail holders that were each put in with looks like 2 screws through the case instead of being glued on. So a bit of an improvement there. They still have just simple sheet metal screws going in from the bottom into posts on the top to hold the case halves together. So I'm going to pop this open and take a look. Now, compared to my Sabtronics 2000, which has a substantial heft to it even with the batteries removed, this feels featherweight. And I'm going to make a prediction that when I open this up there's going to be almost nothing in it. Drum roll, please. Yep, almost nothing. Just one circuit board on the front that has all the electronics and the LED displays and the switches and anything else. The jack for the AC power adapter is wired right up to there, as is the battery holder. And otherwise there's a lot of nada in here. Indeed, this whole assembly can be just lifted right out. Everything's right there. Now, I'm pretty sure we're going to find out when I look at this further that almost all the work is being done by a couple of ICs. Here's a large monolithic IC package that's right next to all the displays, and I bet we're going to find that's a monolithic frequency counter IC that just does almost all the work. The LEDs are going to wire directly into that with no driver electronics. There's a crystal here, which is probably going straight into that. And then there's, looks like 2 more ICs on here, which will be some sort of, at least one of those will be some sort of input conditioning in IC, probably some sort of differential amp. When I look at the schematic again and check out some of the part numbers on the chips, I think that's what we'll find those are. It's all front end stuff. And this is a 78M05. So it's a version of the 7805 voltage regulator that's responsible for regulating the voltage from the batteries or the AC power adapter jack. And there is a hole in the circuit board with the shielded cable coming from the rear of the BNC connector and going straight around and into the board right by the range switch. My first order of business is to find out what the wiring is on the AC adapter jack so I can rig up an appropriate AC adapter to run this off of. Okay, there's with the front panel removed. It's currently only tied to us because of the shielded cable going through there. Otherwise I could separate it more. But there's a nice view of the circuit board. And here's a better indication of what the IC is inside of there. It's an intersil, something or another, ICM 7216 DIPI. And that agrees with the schematic, which just calls it a 7216D. So you get the extra IPI on there and the ICM at the first. So Intersil, of course, was famous for making a lot of specialty ICs, many of which had to do with putting all functions of something in one IC. And if you've seen my series of videos on Heathkit and Fluke digital multimeters, you'll know that Intersil chips are at the heart of those, whether or not they're the generic Intersil parts or proprietary Fluke versions. So that doesn't surprise me that you've got an Intersil frequency counter in there. And then over here we've got a, what is that? A 74 Schottky 196. Right, so that is right here. And then this other part is identified as a, gosh, what is it? I can't even read it. It's a 10116. And that's exactly what the schematic calls it. It's a single IC that has a bunch of differential amplifiers, differential inputs, differential outputs in series. So it's a 3-stage amplifier IC that's using differential all the way through, and then finally looks like it single ends it on the output. So that's the input conditioning circuit, and that's about it. There's a couple of transistors and so on. I'm going to dig into the circuit theory on this a little bit more, but the only thing we have here by way of adjustment is a little trim capacitor there. I think that's a capacitor, and a trim pot over here. Alright, so the trim capacitor is part of the clock for the 7216. It's an it's a crystal clock with a compensating pair of small value capacitors hanging off of each side like you'd normally expect, and then a large resistor and a small capacitance across the crystal. So you can tweak the crystal's frequency ever so slightly with this trim capacitor. So that's the function of this guy. It's the calibration. Now way down here near the front end is that trim pot. I'm looking for a trim pot, and I see a trim pot here. Offhand, not quite sure what that does. I don't think we're going to find calibration instructions in here. I'll try to dig into it a little bit more. And what else do we have? It looks like a couple of transistors are being used primarily as inverters. And one of them is an FET, that's your front end high impedance input. And then there's a bipolar. That's, what's it doing? Looks like it's maybe acting as just a booster for the FET, just on the quickest of surveys. And then here on the output we have a 2-transistor solution coming off the differential outputs of the amplifier chip. PNP off of one, and then a PNP off of the inverted output, and then they're connected up like this. And what's that? Probably a power supply rail. I'm gonna find out that that's what that is, probably. I don't know. I'll dig into it some more, and I'll talk about the schematic at a later point. It's also clear that there are no driver transistors for the LEDs, so the 7216 does do all of that. There are segment current limiting resistors of only 39 ohms each, one for each of the segments in this matrix scan arrangement, and then the common, whatever they are, for each digit are going straight into the 7216, and then the decimal points are also being matrix scanned, and they all come off of this one transistor, which is tied to the gate. So I think that's what that's doing. The gate output of the 7216, it knows when it's gating, and it interrupts the power to the decimal points. So whichever decimal point is turned on in the matrix scan, it'll be flashed by the gate signal. And we saw that during the quick and dirty demo, that the decimal point that was currently on was flashing to indicate how often the gate was operating. So again, I'm going to dig into this some more and then do a schematic breakdown. And if I can figure out what that PSC is, I'll reveal that as well. I have a piece of 16th inch or 16 gauge aluminum, just a scrap, and I've marked out a section to cut and a fold line and another cut line. We'll start with that first. Okay, this is after cutting it out. Now I have to fold it along that line 90 degrees. Okay, there's that. And now I have to measure and drill the through hole. Okay, this is ready for prime time. I've lifted the heatsink off the 7805, which was pushed down diagonally against the circuit board. Obviously that was the plan, and they might have intended to use the normal package where the heatsink is flush with the back of the plastic package, but this is what was actually used here. And so to make it flush, this is going under here instead of on top. And I'll put some heatsink compound on the top of this tab. Okay, folding this up finally. And there's the heatsink underneath. Alright, let's see about getting this back in there. Of course, the battery holder is going to insist on being on the way. And there we have it. Gives it a bit more surface area to sink and radiate the heat from the regulator onto. I don't think it can hurt. Well, I ordered a similar power supply to this one I have for my Sabtronics 2000 digital multimeter. And it's a 1 amp regulated 12 volt power supply from XP Power. From DigiKey I ordered the same exact thing but in the 9 volt output version, which is about 2 volts over the highest voltage the linear regulator on this Sabtronics 8110A will output, but that's only if it's in battery charging mode. So it should be fine, and even though the 2 volt threshold between input voltage and regulated voltage on a 7805, if you starve it a little bit for input voltage, it just stops regulating, but it still passes through whatever's on the input. And since the input is already about the right voltage, it would be okay. But in this instance, it will regulate down to about 6.5 volts when the meter's turned on, and that's what's important. Anyway, even though DigiKey shipped the power supply, FedEx lost it, and I'm tired of waiting for it. So I've just hooked up my bench supply set to 9 volts and hooked up temporarily with a barrel connector. Let's turn it on. There we go. The main thing I want to do is just let it sit there for a moment and see if the heatsink gets warm. Got too much junk on my bench. Okay, it's been on for about 10 minutes. I don't really feel anything warm on the heatsink. I think it'd be fine. Not that I plan to really use this frequency counter for anything, but it's nice to know that if I did, that everything would be good with it the way I have it set up. I feel like I should put a big chunk of lead in here or something, but it doesn't have any push buttons on the front, and that's what usually kills these desktop or benchtop equipments that are more recent, and they don't have the mass of the older units because everything is just, you know, surface mount and lightweight and small, and you push buttons and the things just slide all around. So on here, it's not the kind of thing you change the settings on very often, and when you do, they're just slide switches, not push buttons. So it's not really an issue. Anyway. Where's the holes? There they are. They're a little bit under-engineered, but still functional. So, alright, for a little better demo than I did as my initial tests, I've got the Sabtronics 8110A connected up to my Siglent function generator, which can go to 25 megahertz, a little bit faster than the about half of that the Hewlett-Packard can. So let's go up into the 100 megahertz range here, and I've got this set up as a sine wave with 10 volt peak to peak, and I'm gonna turn the output on. Oh yeah, what frequency do I have? That's important, right? Let's set it up to 1 megahertz. So I'm going to put in 1 and then megahertz. So we're set to 1 megahertz, 10 volts peak to peak. I'm going to turn this on. Okay, I'm going to turn this guy on. Well, 0.99999 megahertz, pretty much there. And I'm going to crank her up to 12 megahertz. And again, we're just a hair under it, very tiny amount under it. So that's the maximum that my generator will put out 24.99971 megahertz. Really close. I'm going to take it back down to about 14 megahertz. And I'm going to see what happens if I change the waveform. We're on a sine wave now. I'm going to go to square wave. Yeah, it's still reading 14. And go to ramp. It doesn't like the ramp. Oh, I accidentally bumped the frequency. That's the problem. I don't know how I did that. Okay, we're back to 12 megahertz here. Now I'll try changing the sine wave to a square wave. Unchanged. I'm gonna go to a ramp. For some reason when I went to ramp, it jumped to 300 kilohertz. I have no idea why I did that. That's kind of squirrely. Unless it can't go any faster than that, which doesn't seem very likely. Let's go to 12 megahertz. Yeah, upper limit's 300 kilohertz with that waveform apparently. That's weird. Wonder if that's a bug. Anyway, it does work on the sine and squares. Apparently there's some issues with this Siglent generator that I have not encountered before. Okay, well let's try it with different amplitudes. So I'm currently at 10 volts peak to peak. Let's take her down to 9 volts, 6 volts, 3 volts, 1 volt, half a volt, 100 millivolts. So it's working over quite a wide range of inputs. Let's go to square wave and see if it still works. Yeah. So the input conditioning circuitry is working pretty well. It's just my function generator is a little disappointing in terms of waveforms at higher frequencies. But I think that we've pretty well proven that this thing works. Down to 1 megahertz. Half a megahertz. 100 kilohertz. And now I can go to the 10 megahertz range. And I'm reading just a hair. It should be 0.1 megahertz, but it's the same error as before. Just the tiniest discrepancy. So, I think this is in good shape. Let's try going to the 0.1 second gate. So now we can see the much faster gate, and the display responds very, very quickly. If I go to the 10 second, we're not even going to get a reading until every 10 seconds. Think, there it goes. Should be 130 kilohertz, and in this instance it's auto-ranged. It didn't stay in megahertz. This is interesting. So I'm in the 10 megahertz range. It says the frequency is in megahertz, but I'm giving it 130 kilohertz, and it's reading it in kilohertz. Aha! That seems to be a bit of a design error. The decimal point is being forced to this position. It really should be at the left. 130 kilohertz should be 0.13 megahertz. And it says it's in megahertz, but it is not. It's in kilohertz. Take that, Sabtronics. Now that's interesting. When I have a 1 second gate, it is reading correctly. But when I give it a 10-second gate, you would think that it would still give me the same reading. It should, regardless of the gate, but it is switching to kilohertz when we do that. Have to give it 10 seconds to catch up. Yeah. It's not always in megahertz. But if I go back to a 1 second gate, then it certainly is. Very interesting. Okay, I'm going to turn the output off, and it should get back down to 0 very quickly, which it did. My wall-wart power supply from DigiKey finally showed up once FedEx figured out where it went. I've marked it as usual, which device it's intended to be used with, and a caution about not leaving it plugged in for long periods of time because it'll just be wasting energy heating up the heatsink inside. Alright, let's look over the schematic, talk about the circuit theory. Just to make it a little more readable, I've done my usual trick of redrawing it in sections in a way that is clearer and easier to describe what's going on. I just hate things like this. That's when somebody thinks it's important to have all the gangs of a switch aligned rather than have a clean layout where it's easy to follow the signals. Anyway, so let me move on to the front end, the input circuits, in other words. Now, just for yucks, this is the Sabtronics 8110A front end circuit, and down below it is the comparable front end from a Heathkit IM2400, which I already have a video on. These came out more or less the same time. The IM2400 came out, I believe, in 1980, and the Sabtronics 8110, I'm not sure when it came out, but the schematic diagram is dated 1979. I've tried to find the history on the main IC, which would be the deciding factor in the unit's age, and as near as I can tell, everybody estimates it as having come out no earlier than about 1977. So that makes sense. If it was new then, give a few companies a year or two to design it in and produce products, and that would add up to the 1979 for this and the 1980. The designs were probably a year earlier than that. Anyhow, I just wanted to see how the front ends compared. The Heathkit, which I've already gone through, uses an FET front end with diode clipping, and that drives a bipolar transistor, and then you have 1, 2, 3 stages of a single IC, and that IC was intended to be the front end of any device that was going to be using a differential transmission line. So it's really a differential transmission line receiver amplifier IC. It's the MC10216. Actually, the Heathkit used the 10216, whereas the Sabtronics uses the 10116. Nearly identical parts, slight differences. Anyway, so they receive the signal and then they run it through the multiple stages. I haven't looked up the data sheet to see if there's any actual amplification going on here, or if it's just really buffering and conditioning. Although this one, the Heathkit one, does have what appears to be some kind of feedback resistor on the last stage, so that may be some gain. And then finally there is a little transistor circuit that provides the single-ended output signal that goes into the counter. So looking at the Sabtronics one, we have a selector switch, a 3-position selector switch, which is the 10 megahertz and 100 megahertz selector switch. And if you bought the add-on prescaler circuit board, then it could go up to 600 megahertz. Some versions of the 8110A or the 8110 said 600 megahertz on the front panel for the third switch position. Some of them say PSC, which is short for prescaler. Maybe that was hedging their bets in case they came out with a different prescaler that could handle maybe even more frequency range, and they didn't want to redo the front panels. I'm not sure. Anyway, if you selected the 600 megahertz or prescaler, you immediately took the input jack and routed it off to the prescaler circuit. Otherwise, either the 10 megahertz or the 100 megahertz came in at this point using the same circuit. There's a DC blocking capacitor, a little filter circuit, front end loading. It's a 1 mega ohm input impedance, which is pretty typical for frequency counters, and a little bit more front end conditioning and diode clamping. Once again, very close to what Heathkit had. DC blocking capacitor, 1 mega ohm front end load resistor, parallel capacitor resistor, and then the clamping diodes. Very much like this. The only difference is that the Sabtronics has this where the Heathkit does not. Then you've got, again, an FET front end. Here the circuit differs a little bit. On the Heathkit it went from the FET into an NPN transistor, where on the Sabtronics it's from the FET into a PNP transistor. But what you're really trying to do is come up with a differential front end for the first stage of the buffer amplifier. And it's done in slightly different ways between the two, but then it's very similar. Now, Heathkit chose to use the inverting output of every stage to go into the inverting input of the next stage and go all the way through that way. Sabtronics, on the other hand, just flip them upside down. So the first stage you come in here, and then the inverting output of the first stage goes into the non-inverting input of the second stage, and the same thing happens going to the third stage. It doesn't really make any difference. It's just a balanced signal. And when you convert it to single-ended at the end of the day, it's immaterial whether you invert or not in these stages. Probably it comes down to convenience on the circuit board. Once again, there's a feedback resistor on one of the stages. This time it's the middle stage. Presumably that offers a little bit of gain. These other ones I think are just buffers. And all the resistors are just loading. So here you've got the inverting output has a load resistor to ground, and from the non-inverting output a same value load resistor, and then the same thing happens loading the second stage, and the same thing happens loading the third stage. Now that's really bugging me that I did it that way. Let me fix that. There, mo better. I made it the same way I did the other stages. And then both of them end up going into transistors, the outputs of which are combined, and so you've unbalanced or made it single-ended the output signal. And then at that point there is the same switch again. And I've added the switch positions on there. So once again, if you're in the 10 meg or the 100 meg range, it's all the same, and you just come out and go directly into the counter circuit. Whereas if you were in the PSC prescaling position, now you take your signal from the output of the prescaler. Remember that if we were in the prescaler position up here, the input signal from the input jack skips this whole front end and goes out to the prescaler, which has its own front end that's optimized for higher frequency ranges, and it also has a counter or frequency divider on it, which divides down by 10. So it's really a 1000 megahertz range being divided down to a 100 megahertz range, except that due to component limitations it can only go to 600. But again, they might have allowed for future versions to be able to go faster, and therefore just started calling it PSC instead of being specific. So I was starting to explain the input conditioning or front-end circuit of this frequency counter, and I felt like I was copping out by just glossing over the details. So I just dug into it a little bit more, and I think I can explain it a little better. There might be some small mistakes in what I'm saying, but reverse engineering it as much as possible. So I've cheated a little bit here. I left off the switching that happens between the input jack and the circuit here, but it's just routing circuitry. Assume that this is connected at this point. So the first part of this is a DC blocking capacitor. So its primary purpose seems to just be to block any DC component and only let AC through. Now this here, it's not a filter. I think it's working in conjunction with this capacitor to form a capacitor-capacitor resistor voltage divider. It certainly has that effect. And I worked out the capacitive reactances at various frequencies from very low up to the counter's maximum input of 100 megahertz. And it always balances out. The voltage here is always just a hair below the voltage applied here. So it's, if you put in 10 volts peak to peak here, you'd always get something like 0.998 volts peak to peak here. So the thing is that if you didn't have this and just had this 1 mega ohm input loading resistor, which nominally sets the input impedance of the counter, I think it would work the same way. There wouldn't be any appreciable effect on the signal. And indeed, looking at the Heathkit version, which is otherwise very similar, it doesn't bother with these. So I'm not quite sure what the rationale was for having them in there. I don't see that it really helps anything because the voltage is unaffected. Okay, so we've got the loading resistor. This provides a 1 mega ohm load. Okay, now we have diode clamping here, and that is just restricting this signal to no more than the forward voltage drop of a forward biased diode. One or the other would be conducting. If you get the signal more than, say, about 0.6 or 0.7 volts away from ground, or 0 volts. So what this is doing is it's limiting the input voltage. It's protecting the meter circuit if you hooked up some really crazy voltage on the input, but it also just makes everything equal, essentially, whether you're putting in millivolts on the input or whether you're putting in a couple hundred volts on the input. By these diodes, it always gets knocked down to no more than plus and minus 0.6, 0.7 volts. So it's the great equalizer, essentially. If you do put in a higher voltage here, then there could be quite a lot of current coming in here, getting essentially shorted to ground through one or the other of these diodes, and that would cause a lot of current. So this 100K resistor here is there to limit the current when one or the other of these diodes is conducting, in its job of limiting the voltage at this point. Now it has a compensation capacitor across it, and this makes the combined impedance of this drop to a quite low value at the maximum frequency of 100 megahertz. But I'm not quite sure why it needs to be dropped that much, but that's the way it seems to work out, unless I made a mistake. Okay, let's look at this front end circuit. We have an input conditioning amplifier chain, which consists of 3 stages of this IC that we're calling Z3 here. And what we need to do is get it something that it views as a differential input, because these are differential amplifiers or differential buffers. I couldn't find a data sheet that actually gave a gain specification for this IC. A similar looking IC from the same manufacturer, a triple differential amplifier in an IC, that one had something on the order of 24 decibels of gain per stage, which you could dial down or dial up by putting on a feedback resistor. For this particular IC, I didn't see any gain specification, so I don't know if that means it's negligible or if it's totally up to the programming or what. There was no information in it about gain at all. I'm going to presume there's some gain in each one of these stages. So this FET here is an N-channel depletion mode FET. So whether it's depletion mode or not affects the way it responds to the input voltage. In this instance, a negative gate to source voltage causes the source to drain to be a high impedance, so it acts like an open circuit, while a positive gate to source voltage makes this act like a closed switch. So if you have an input signal here at this gate of 0 volts or some negative voltage, the gate to source is, I think, negative, so the FET is acting open. You've got this 250 ohm resistor, which is, it's really a 500 ohm trim pot, but we're presuming that it's set to mid-range nominally, so I'm calling it a 250 ohm resistor. This being open here, this resistor allows V plus to pull the base of this transistor Q5 high, and it being a PNP, that turns it off, so it's not in the picture either. So both of these transistors are essentially open. Well, we've got this differential input on this amplifier, and so now it's a non-inverting input, or its positive input is tied to ground through a pretty low resistance of 220 ohms and 100 ohms. So, you know, it's basically 0 volts. And since at this point there is no modulation of voltages here, since the input signal cannot get through to these components, this is basically DC. So these two capacitors, a 100 microfarad and a 0.1 microfarad, might as well be not there. And therefore this relatively low resistance, 470 ohms, is pretty much just tying these two inputs together. So this amp is not looking for a particular voltage here or here. It's a differential amp, so it's only looking at the difference between these two inputs. With both of them basically being tied to ground, the input is essentially 0, and therefore it's outputting nothing, or some very small amount of differential signal on its output. So now if you've got the other scenario where the input signal here to the gate of this FET is above some fairly low voltage, then that causes the gate to source voltage to be positive enough that anyway that the FET is closed between these points, or at least at a much lower impedance. And that forms a voltage divider of this trim pot and this 100 ohm resistor down here. Since this is about 6.4 volts up here on V+, that ends up with a voltage here of roughly 1.8 volts at this junction here. And with this point here being pulled to 1.8 volts, that is applying 1.8 volts to the base of this transistor, and its emitter is at 6 some odd volts. So there is a sufficient base emitter voltage here to cause this transistor to conduct, and therefore it's pulling this signal up to V+. So not only is it being pulled up by this, but even if this weren't happening, the fact that this transistor is turning on all by itself, it would be trying to apply 1.8 volts out to here. So this transistor here is basically driving this one, which actually is the main contributor to the voltage here. It's basically nearly the positive power supply. But then we have a voltage divider here comprised of this 470 ohm resistor and whatever the capacitive reactance is at the frequency we're talking about. Remember, it's switching back and forth between these two stages of what I described previously in this stage. So this is going to have some resistance, or it's going to have an impedance to it, and that combined with this is going to result in something less than this voltage. And it's not even that important what it is, because now you have a differential voltage. You've got just about the positive power supply here and something less than that here, and therefore it's a differential voltage, and therefore it'll be amplified by whatever the gain is of this stage and output some voltage greater than that. So I think basically what all of this is doing is it's taking the trimmed voltage, which can be no more than plus or minus 0.6 or plus or minus 0.7 volts here, and it's giving it a very high impedance. That's what the FET is contributing. And then by the action of this circuit, it's resulting in either no differential voltage here or some differential voltage, and we're switching from a single-ended circuit here to a differential signal. And so this amplifier is either seeing very little on a low signal and something on a high signal, and therefore it gets propagated through with some gain. So essentially you're turning a trimmed low signal to a differential higher signal, and that may or may not be enough to reach the extremes of the output swing, depending on how big the signal is and what the amplification here is. And it's okay if it hits the rail. In other words, the rail is the maximum voltage the output can swing because of the power supply. And the power supply on this IC is just plus 6.4 or whatever V plus is on the positive, and then the minus side of the supply is just tied to ground. So it can't swing more than 0 to around 6 volts. So it may be saturated at this point, maybe not. Either way, it's still a differential square wave. And the amplitude should be pretty much unaffected by what the amplitude of the input here is. All the actions here, the attenuation and then the buffering and converting to differential signal, and the gain here is going to result in this being a pretty much consistent voltage going on and off at the frequency of the input signal. So all in all, we've turned a totally unknown input signal, or its voltage is unknown, into a relatively known stable voltage swing signal here, and it's differential instead of single-ended. So here's the rest of that circuit on page 2. This is the differential output from the first stage we just looked at, and it's applied to the second stage. Also looking at a differential input. Doesn't care what the actual voltages are as long as there's a difference between them. There is a resistor tied from the inverting output to the non-inverting input, and while I couldn't find anything in the data sheets on this, I'm guessing that that results in something akin to negative feedback on an op-amp. And this isn't really exactly an op-amp. It's, I think, more elaborate than that, and it's also differential. But I think the result of this resistor is to set some sort of gain for this. And I believe what it's doing is it's further boosting the input from the first stage until you really do have essentially saturation here. Possibly the action of this resistor is to act as a damper if the signal here is already so high that it's hitting its peak out here. Then maybe this backs off the gain so it doesn't hit it so hard. I'm not really sure, but I'm pretty positive it has something to do with adjusting the gain here for the optimal signal here. Finally, we get into the third stage, and it's, I think, identical to the first two stages in what it is by itself, but here it has feedback resistor from the negative output to the negative input, or inverting output to inverting input. And because this is differential, I think this counts as a positive feedback, as if this were an op-amp with positive feedback. And that converts this from a gain stage into a Schmitt trigger. So it's causing a real hard snap action. There might be some sloppiness to the waveform here, and the action of this, I'm pretty certain, is to convert it into a really really clean square wave. And again, probably the full voltage of the power supply on this IC would be the voltage swing. And so you've got a square wave of about 6 volts peak to peak, and it's going to be very clean and really straight up and down edges to it coming out of here. So once again, all that junk in the front end has basically been to A, protect the circuit, and B, convert a very unknown range of input voltages and impedances into a very known and predictable, very clean square wave signal here. It's still differential, but its frequency is the same as the input signal. And finally, we have to get from the differential signal to the single-ended signal of an appropriate voltage to feed into the frequency counter IC. So we have these two PNP transistors. They almost look like they're in parallel, but not quite. Their emitters are tied together, and through a 24 ohm resistor to the positive voltage supply around 6 volts. This one's collector is tied directly to ground. This one's collector is tied through a 75 ohm resistor to ground. And so what's happening here, when the signal is supposed to be high here, in other words, when it's at a high voltage differential, pin 3 is positive, and it's defined as being positive because it's higher than the voltage at pin 2, and that's essentially the square wave is high at that point. So the positive voltage here holds the gate, or the base of this transistor high, and that turns it off because it's a PNP transistor. So it's essentially open. It's like it's not there as far as the rest of this is concerned. And since at the same time this is high, this is low, and it can't get any lower than 0 volts because of the power supply, it's essentially 0 volts here, and that turns this transistor on, and therefore it's forming a voltage divider out of this 24 ohm resistor and this 75 ohm resistor. And that results in approximately 4.8 volts, or nearly 5 volts here. And that's a good voltage for the frequency counter IC to treat as a logic high. So it sees that as the top side of the square wave signal. And it's certainly a voltage it's looking for it to be that. Now when the waveform is in its opposite half, the Z3 differential voltage is negative. In other words, the pin 2 voltage is higher than pin 3. That means pin 3 is low, and that turns Q6 on, and that pulls this point here to ground through this 75 ohm resistor, which is of negligible consequence, into the impedance of this IC out here. So we've essentially put a 0 volt signal out here. And also at the same time, pin 2 is high, and that turns off Q7, so it has no effect on the output. It's like it's not even there. So once again, in that half of the waveform, this is 0 volts. So this is switching back and forth between about 5 volts, just under that, and 0 volts ground at the frequency of the input. A nice single-ended signal of the appropriate voltage. So there's also a little bit of circuitry up here. On here, this signal here, which is the positive power supply for the whole front end circuit, it's a switched V+, and that even goes into the PSC module along with the ground, and that's for power to the PSC. And that whole thing comes from this interesting little transistor circuit. So if you're in the 10 meg range, you power this point, 10K over a 10K voltage divider, and that feeds this transistor. Normally this transistor, or this resistor, pulls the base low, so this transistor is turned off, which means it's not conducting, which means this resistor can pull this point up, and if that's pulled up, then this PNP transistor is turned off. It's not conducting, and therefore this point is unpowered, and as a result none of this front end circuitry is working. Without power it can't. But again, that only happens if you have not selected this range. And if you have selected this range, now V+ is connected to this. It raises the voltage here, turns this transistor on, which now pulls this point down to ground, which makes this a low, and the low turns on this transistor, which now conducts from V+ and supplies power to this whole front end circuit. So that's in the 10 meg range, but in the 100 meg range, something very similar happens, but without the transistors. In the 100 meg range, you just take the V plus directly, skip the transistor circuit, and go right to the power rail here. So why did they do that crazy thing? Why not just tie the 10 meg and the 100 meg together here and power this rail, since it's going to be used? Well, I think they did that because they're pulling a bit of a stunt with the front end frequency divider, where to get it to work properly, they want to manipulate the load input. And to get the load input, they needed a point that's inverse from the 10 meg. So it has something to do with that. I haven't worked out every detail of it, but I guess they figured since they're going to be using an inverter here, they could just carry it through and also switch the power supply that way. Seems like an odd decision, not the way I would have done it probably, but they probably had their reasons. So I think we've covered all of that. Let's move on to the guts of the matter. Alright, here's the main part of the schematic. The whole meter, except for the front end, is built around an intersill part. Now, if you've seen my other videos on all the Heathkit and Fluke digital multimeters, you'll know about the intersill 7106 and 7107 monolithic digital voltmeter chips / display drivers, where they packed almost all the guts into a single IC, which made it very easy and reliable to do equipment of that type. Well, Intersil also did the 7216, which came in 4 flavors, the A, B, C, and D suffix versions. This is a D version. The A and the B were more powerful versions of the chip. The C and the D were frequency counter only, so they did all the frequency counter functionality but nothing else. Whereas the A and the B versions had the ability to do things like measuring the period, comparing 2 inputs and giving a difference in frequency between the 2 signals, and things like that. It probably also did a totalizer. So if you were going to build a normal frequency counter with all those functions, which are common on benchtop frequency counters, you would also expect period and totalizer modes, and on the nicer ones, the ability to display the difference between 2 different frequencies. So you would pick the A and the B versions of the chip for that, but those were significantly more expensive ICs, and the C and the D versions of the ICs only did the frequency counter part without those other bells and whistles. The Heathkit IM2400 also used the ICM 7216D. So the chip has internal circuitry for the oscillator and handles all functions related to the oscillator, including the counting function and gate generation, because that's the essence of a frequency counter. You have some very accurate gate that's usually derived from dividing down many times a higher frequency source like a crystal oscillator, and that gets you a very precise gate or window of measurement time. So you would zero out your counter, and then the gate would allow the counter to start counting, and it would count the input signal for a very tightly controlled period of time, again specified by the gate signal, and then it would shut off, and whatever number was in the counter was the frequency, and that would get displayed, and then it would reset, it would re-gate and do it again. And it was very common to have the gates happen at different periods, or intervals rather. For example, 0.1 second, 1 second, 10 seconds. So you could have it update 10 times a second, you could have it update once a second, you could have it update every 10 seconds, things like that. So all those functions can be handled in here and it includes all the divide down of the oscillator to get to the lower frequencies needed by things like the gate, but it also handles the display multiplexing and other internal functions off that same crystal. So this is pretty typical. You just got the so-called oscillator out and oscillator in pins. There's resistor across it, the capacitor across it, the crystal across it, and then from each side there's, as this is very textbook here, very classic, a fixed capacitor to ground on one side of the crystal and a similar value adjustable capacitor on the other side. And by adjusting this one capacitor, you could force the crystal to oscillate at slightly different frequencies than its nominal frequency, and that's how you would calibrate the thing. The chip requires a positive input voltage, and here it's just coming from V+, and I'll talk about the power supply later. And there's a capacitor to ground just to filter that. It's actually a small capacitor and a large capacitor. This one is dealing with higher frequency noise, and this one's dealing with lower frequency noise. So the positive power supply, what we're just calling V+ here, is applied to the VDD input or V+ input of the chip, and then the VSS or ground connection to the pin goes to circuit ground, so that's very simple. There's also a reset which is not being used in this Sabtronics meter, so that's just tied to the positive power rail to disable the reset. There's also a hold function where you could hold the count. That's not needed here, and to disable it, it's tied to circuit ground. There's an input called input A, and you may wonder, why is it called A? Why is there an input B? Well, they use the same terminology, the same nomenclature for all the models of the chip, and only the A and the B versions of the IC had dual inputs, in which case they would have an in A and an in B, but the D model only has the in A. And this is rated up to 10 megahertz. That's all it can handle. So if you want to measure higher than that, you have to do some sort of pre-scaling. And there's a control input. And when that's connected to part of the multiplexing circuit, I should step back. All inputs to the 7216 IC, except for the frequency input, I think they're all multiplexed. It's a 28-pin IC, not a 40-pin, and I think they did that just to keep it small so it would fit into smaller equipment. But because of that, it's kind of short on pins, and the majority of pins on the chip are used to multiplex the 8-digit LED display. The digit outputs, of which there are 8, and the segment outputs, of which there are 8, including the decimal point. So that's 16 pins right there that are just tied up directly with multiplexing the LED display. And what they did is something a little bit clever. They also multiplexed all of the inputs that are used for selections and mode control and things like that. Really the only inputs which are not multiplexed are things like the reset, the hold, and so on. And actually, those might be multiplexed too in some configurations. Certainly the input from this input signal is not multiplexed. That wouldn't work. But when we get into that part of the circuit, I'll show how the multiplexing of the switches works. But anyway, let's go into the input here. The input from the front end amplifier comes in to this other IC, which is a 74S196. This is actually a dual counter IC. It's a divide by 2 counter and a divide by 5 counter in one IC package. The input from the amps goes into clock 1, which is the input of the divide by 2 circuit, and that only has one output, and that's the QA, and that just wraps around and feeds into the clock 2 input, which is the clock or the input of the divide by 5 circuit. So it's a divide by 2 followed by a divide by 5, resulting in a divide by 10 counter. The 74S196, not to be confused with the 74196, the S version is rated up to 100 megahertz. And this is used by both the Heathkit product that I mentioned earlier and this model, and probably a lot of other ones that use this IC. I think it's probably the IC that they recommended in the data sheets as a good choice for this. So we're going to either divide by 10 or we're not. And how do we decide if we're not? Well, remember that the input switching does not differentiate between the 10 megahertz range and the 100 megahertz range. It's all treated the same up to that point. And also recall that the goal is to condition the input frequency so that it always looks like a 10 megahertz signal or a 10 megahertz full range signal to this IC. So either we're going to divide by 10 or we're not, but the input signal doesn't have a switch going around this. On the Heathkit version, they either went through the chip or they went through a gate that would either use the output of this chip or it would use the input. Well, they saved the cost of a chip here and did something a little cleverer. So there's a pull-up resistor elsewhere in the circuit that pulls this high, which means it's not in load mode. But when you put the meter in the 10 megahertz position, then this gets pulled low, which puts the chip in load mode. And I won't go into all the details of how the innards of this work, but the effect of that is that it stops working as a counter and it just passes the input through to the output. So that's why in the 10 megahertz range, the signal goes into this chip and comes out of this chip unchanged. It does not get divided by 10. But if you're in the 100 megahertz range, then this is high, it's not in the load mode, and it starts behaving like the divide by 10 counter we expect. So that's how that's working. Just a little more details on how this works after a little bit more reverse engineering on my part. Here's kind of a internal view of that IC. It has a top section. There's a dashed line there. This is a divide by 2 counter. And then there's a separate counter, which is a divide by 5 counter. And each one of those has a clock. Clock 1 feeds the divide by 2 counter. Clock 2 feeds the divide by 5 counter. Together they act like a divide by 10 counter. The output of the divide by 2 is called QA, and then the 3 outputs of the divide by 5 are called QB, QC, and QD. We're only using the QC output here. The output of the QA, or the QA output, is fed back around to the clock 2, or the input of the divide by 5 counter. There is an input circuit for each of the outputs. So QA, B, C, and D have corresponding inputs A, B, C, and D. In this application, the A, C, and D are not connected to anything, and they probably float high or low depending on the internal circuitry of the IC. I suspect that they float low because the original Sabtronics schematic shows those 3 pins actually tied to ground, but they are not on the circuit board. That suggests that they found out they don't really need to tie them low to have them effectively be logic low. Anyway, so normally the input signal comes in, it goes through and gets divided by 2, then gets divided by 5, or it's divided by 10 in the aggregate, and you end up with a frequency on the output that's QC, which is 1/10 the frequency of the input frequency. So if you put in 10 megahertz, you'd have 1 megahertz on the output. And that is how the maximum 100 megahertz input of this frequency counter gets divided down to the 10 megahertz, which is the maximum frequency that the counter IC is expecting to see. Now, when we're in the 10 meg range, then we don't need this counter or this divider, and there are several ways to bypass it, but it's a little bit clever, I think. The input frequency is also connected to the input C, and when the range switch is in the 10 megahertz range, it actually activates this load input by pulling it low. This is a negative acting input, and when it does that, whatever data is on the A, B, C, and D inputs gets written directly to the outputs, overriding whatever is trying to come out of the counters. So if we have pulled this load input low in the 10 megahertz range, then the input frequency just comes down here, comes into input C, gets directly coupled to output QC, and goes on its way without being altered or divided or anything. So that's how that operation is handled. So let's look at the display. So we have a total of 8 digits of 7-segment LED displays. I mentioned before that there were 4 versions of this frequency counter IC, the A, B, C, and D versions, and that the A and B were the fancy full-featured versions, and the C and D were the stripped-down frequency counter-only versions. Well, the difference between an A and a B, or a C and a D, is whether they're set up to drive a common cathode or a common anode LED display. So the D version is designed to work with common cathode displays, and if it were the C version, then it would work with common anode displays. And the same thing applies to the A and B versions. One is for common cathode, one is for common anode. So we've got a common cathode version of the chip, and indeed we have common cathode 7-segment LED displays, which is the FND 357, an extremely common family of LED display modules from that period of time. Seems like almost everything used them. And you can still buy the darn things today. They're not made anymore, haven't been for a long time, but so many were made that they seem to be in fairly ready supply from surplus, as well as ones that have been pulled out of equipment and checked and are being sold. They're not all that rare, although they do tend to die after a while. If you have these things on circuits such as digital clocks, it's not uncommon after the decades have rolled by for various segments to be burned out on them, or just be weak, not lighting up very well. Anyway, so the chip outputs 7-segment outputs, A, B, C, D, E, F, G, and a decimal point, so a total of 8 signals. And because you've got common cathodes, that means that the current is flowing into the anodes of the display, and that means the current is coming out of the IC here. So it's sourcing the current, and that comes out. It goes through these resistors, which are not really required, by the way. The chip is rated up to 12 milliamps of drive current on each of these pins, and that's more than enough to drive the FND 357. You don't need any other buffering, but it looks like the Sabtronics engineers decided to throw in some small value 39 ohm resistors, which is just cutting down the current a little bit and probably making the chip run a little cooler and probably made them feel a little better. Or maybe they just thought the display looked a little too bright as it was directly driven. I'm not sure, but the other meters I've looked at, including the Heathkit one, which also uses the same kind of displays, they did not use the dropping resistors here. Anyway, so then once you come out of the common cathodes on each of the display chips, those all have their own return lines back into the chip, D1, 2, 3, 4, 5, 6, 7, 8, which some diagrams perversely called D0 through D7. It's a classic case of somebody being so obsessed with digital nomenclature that they're using something that makes no sense. When you're dealing with binary values, starting with 0 makes sense. When you're dealing with which digit you're looking at, a digit 0 makes no sense. So, but you'll see that anyhow, and I've shown both versions here, just depending on which other documents you're trying to correlate this with. So again, it's multiplexed, and all that means is that one at a time, the chip here turns on one of these 8 inputs so that current can go into it, and then it lights up or it energizes all of these segments which need to be turned on for that particular digit, and does that for a short period of time. Then it turns off that input here and turns on the next one, allowing current to flow out of that next digit, and then it turns on the pattern of segments for that digit and repeats and goes through all of them, then does it again, and does it so fast that the persistence of vision of the human eye makes it look like all of them are on at the same time. So I said before that there are some inputs which are part of the multiplexing, and this is the case. There are some general inputs like range in and external decimal point in and control in, that when those are tied to different digit points on the chip, have different functions. So if you tie the control input to D3, then when the multiplexing is going on and it's turned on D3, the logic in here looks to see if this is connected, and if it is, then it takes appropriate action. If it's not, it does something else. In this particular situation, when the control input is connected to D3, this enables external decimal point control functionality. So normally this chip even handles the decimal point positions automatically, but it's common in these meter circuits to want to manually control, or at least have some authority over the decimal point positioning. And so by hooking this control input up the way it is, this chip is giving a certain amount of control over decimal point position to the external circuitry instead of handling it all on its own. The other two things that we're doing here are we're bringing in the range. The chip has to know which range we're in, and by range it means the gate, really. It's not the frequency range, it's the gate. So we have a gate switch here, which is in 4 different gangs, and it's the 0.1 position, the 1 position, and the 10 position. Those are all in seconds, so gate at 0.10 or 0.1 second, gate at 1 second, gate at 10 seconds. And as I said before, that means that it will do a new count and update the display 10 times a second, or once a second, or every 10 seconds. And those can all have their own advantages and disadvantages, and it's common to have at least a couple of those on any frequency counter. By comparison, the Heathkit frequency counter, which is very similar to this Sabtronics one in many ways, except that it's in a handheld case, only has 2 gates. Anyway, so the range input goes through this 10K resistor, and depending on which position the switch is in, those are connected over to the D2, 3, and 4 inputs of the matrix scan circuit. So once again, when the chip is multiplexing and it turns on D2, in addition to sending out the appropriate segment data for D2, it's also looking at the range input to see, oh, did that signal come on at that time? If it is, then it's connected over to D2, and from that we know that the gate should be 0.1 seconds. But if it gets this signal when a D3 is turned on, then it knows you're in the 1 second gate, and so on. Now, as far as figuring out where the decimal points are supposed to go, it's a combination of which frequency range you're in, the 10 megahertz, the 100 megahertz, or the 600 megahertz or prescale, and each of those positions goes to its own gang of the gate switch, and those are progressively offset by 1 digit. So the first one, it actually is kind of a rolling progression. So the one for the 10 megahertz, if you're in 10, that comes from D2. If you're in 1, it comes way up here from D7, and if you're in 0.1, it comes from D6. But if you're in the 100 megahertz position here, then 10 comes from 7, 1 comes from 6, and 0.1 comes from 5, and so on for the next range, which is, again, as I said, really a 1000 megahertz range, but due to frequency limitations on some components, it's limited to 600, even though the rest of the circuit thinks of it as a 1000 megahertz range. So that's how the decimal point is messed with. We're still letting the chip handle a lot of the decimal point functionality, but at least by doing this, we're letting it know which frequency range we're in, therefore which prescaling we're doing up here, and also which gate we're in, and that factors in. There's also leading zero blanking on this IC, so it always knows where the decimal point is, and it always turns off all digits to the left of the decimal point. So you'll never see 000.0, some number. There will not be any zeros to the left of the decimal point. And I also added a chart to my sketch. The switching over here that I've already talked about, essentially what's happening once we have taken the control input here and connected it to D3, as I said before, that's allowing the external circuitry to specify which decimal point should be turned on. So that works out. I made this little table. In the first three here are in the 10 megahertz range. If you're in the 0.1 second gate, the decimal point is here. In 1 second, it's here. In 10 seconds, it's over here. The next three are 100 megahertz. For 0.1 second gate, it's here. For 1 second gate, it's here. 10 second gate, it's here. And for the 600 megahertz or prescaler range, even if that module is not installed, the decimal point is still being controlled. So in 600 megahertz or prescale, in 0.1 the decimal point's here, in 1 it's here, in 10 it's here. There's really only one other part of the counter circuit that I want to talk about, and that's a little nuance that to let you know what the gate is and when it's happening, the Sabtronics engineers decided to have the decimal point flash at the gate rate. So if you're in the 0.1 second gate rate, the decimal point's practically flickering. And if you're in the 1 second gate, then the decimal point is flashing once a second. And if you're in the 10, then it's flashing once every 10 seconds. And the way that's accomplished is this chip actually has an output that says when it's doing the gate. Every time the gate opens and closes, if you will, or resets, it outputs briefly, and that goes into this transistor, which takes the decimal point segment driver and conditions it. So the decimal point can only go through this way if you're currently gating, because on gate this gets pulled low, and this is a PNP, so going low on the base turns it on. So again, if a decimal point is going to be displayed in position or in any of the positions, and it's gating at the moment, then the transistor here causes that to pulse at the moment. Remember that the frequency of the gate is not related to the frequency of multiplexing, so it's not like it interrupts the decimal point all the time. It only does occasionally whenever the gate occurs. And that comes through and goes all the decimal points except for one. So I want to clarify how this flashing decimal point works. The thing that's called gate output, it probably makes it make a little more sense to call it measurement in progress. So while a measurement is in progress, in other words, the time when the counting is taking place, accumulating a count before displaying it, this signal is low. And a low turns this transistor on, allowing the decimal point signal to pass through and operate whichever decimal point the chip wants to have on. At the end of the measurement, in the interval between measurements, the signal goes high, which turns the transistor off, and whichever decimal point the chip is trying to operate will briefly shut off. So that's how that works. And the reason why the decimal point in position 8 is not conditioned by the transistor is because that decimal point has a special function of being the overrange indicator. So we don't want to have it operate in a squirrely way. The data sheet doesn't actually say how it's indicating, but I think it must flash or do something like that, and therefore it would be confusing. So that's clearly why the unadulterated decimal point signal is used for the decimal point on digit 8. Okay, I saved the power supply for last. So the 8110A can be powered off of a battery consisting of 4 C cells. It can be either alkaline or it can be NiCad, and you can also connect an external power adapter, which is kind of loose and not regulated in its voltage, but it's applied to the input of a 7805 voltage regulator, a common, very standard 5-volt voltage regulator of the linear type. It seems like everything used those at that period of time, and they're still extremely popular. The output runs through a diode, and I think the reason for that is you can blow up a voltage regulator in this family by having more voltage at the output than there is on the input. And you know, depending what is going on here and what's going on here, you could potentially have a lower voltage here than you do on the batteries under some weird situations. And if that happens, then it would force current backwards through this and would damage it or totally destroy it. The most common way of dealing with that is just to put a diode outside feeding backwards from the output to the input. But Sabtronics decided to use a in-series diode going this way just to prevent current from going backwards at all. And here's one gang of the power switch. There are 3 other gangs. One of them is here, and another one is here. And actually, I think it's this one is doubled up, so it's actually 2 gangs in parallel, but I'm just showing it as 3 gangs of the same switch. Now normally on a 7805, the reference pin is connected directly to circuit ground, and when you do that, then the output is 5 volts. But you can offset it. You can put a resistor in here, you can put a Zener diode here, you can put some diodes facing to ground, as is done here. Any of those approaches can result in offsetting what the 7805 thinks of as ground and making it higher and by doing that, it makes its output higher. So there are actually 3 1N4148 diodes in this series path, and each one has a 0.7 volt forward voltage drop. So if you had all of those, it's a 2.1 volt offset, which means that the output could be as high as 7.1 volts, which is 5 plus 2.1. And if you short out one of the diodes with the power switch, then you only get 2 voltage drops, or 1.4 volts offset, which you add to 5 volts and you get 6.4 volts. So the output is either 6.4 volts or 7.1 volts. It's 6.4 when the power switch is on, and thereby shorting out one of these diodes. If the power switch is off, then it's 7.1 volts here. But then you have a 1N4001 diode, which has a forward voltage drop typically a little bit higher, and it's common for it to be about 0.8 volts. And indeed, in this circuit, I measured it as being 0.8 volts while the meter's powered and in operation. So you have to subtract that now from the voltage here. So if the meter is on and you have 6.4 volts here, you subtract the 0.8 volts and you have 5.6 volts. If you had 7.1 volts here when the meter is switched off, now you have 7 volts here. So that voltage boost deal is primarily because when the meter's off, you want to charge the battery faster. And indeed, there's a 6.8 ohm resistor going from this point directly to the plus side of the battery, the other side of which is connected to circuit ground. So when the meter is off, again, this only works if you've got the external power adapter plugged in, so there is a source of voltage here. And if that's the case and the meter switched off, now you've got 7 volts applied through a 6.8 ohm resistor into the nominal 6 volt NiCad battery pack that's here. And again, you have to make sure you don't put alkalines in here when you're using the external power supply. And the label on the back of the frequency counter actually says that. It says, you know, don't have non-rechargeable batteries in here. I forget exactly what it says, but it's a warning about that. And then there's also a page, it's an addendum to the manual, which, and they also have one that's taped onto the front of the manual, right on the front cover. Apparently they must have had a lot of people blowing these things up. You know, if you connect an external power adapter and you have alkalines in here, or some kind of non-rechargeable battery, or as they say, disposable batteries, then you're going to have a fire. Or something bad's going to happen, because those are not designed to be recharged. There's another gang of the power switch here, and one here. And if the meter is turned on, now you bypass this resistor. But when the meter's turned on, it's only 5.6 volts. So now you're applying 5.6 volts to the battery directly. So it's not much of a charge. It's actually less than the nominal voltage of the battery. Of course, if it's NiCads, then they don't really come up to 6 volts anyhow. They're a little bit shy of that, so it's what Sabtronics thought was an appropriate voltage to be applying. And the circuitry downstream here, the 74 LS196, the ICM 7216D, and the buffer amplifier circuit are all fine. None of them care exactly what the power supply voltage is. It doesn't change their operation, and they are not TTL. They don't burn out if it's more than 5 volts. And I think just for convenience in wiring the switch, they've taken the off position and wired it back to the wiper of the switch. This does nothing. It just makes the wiring of the switch easier. And then finally, this gang of the switch, if it's in the on position, it lets power come out of the battery or out of the voltage regulator and go on to the V plus and power everything in this circuit. So that's the power supply.